Alright, so let's solve the last few types of problem that occur in chapter 9, I believe. Um, first, first of all, the only difference, this is exactly the same problem that you saw um, in chapter 9, except this time, instead of giving the population standard deviation, we're now given the sample standard deviation, S, right here, instead of sigma. And what that means is when you're given the sample standard deviation, you want to use the t-test statistic instead of the z-test statistic. So let's go ahead and solve this problem. Everything else is the same as what you saw in the last problem of chapter 9 quiz. Anyways, what is the null hypothesis? And we see that every quarter pounder is supposed to weigh exactly 0.25 pounds. Whenever you have that exact weight, the null hypothesis is always equal to that weight. So this would be E. And the alternative hypothesis will always be F, or not necessarily F, but not equal to that weight. So we take a sample size of n and determine the following information below. The significance level is 0.05. So find the value of the sample test statistic. So you want to go to your equation sheet, and this is an updated equation sheet that you'll have for your final exam. It's now available for download in the same place the old equation sheet was. Anyways, under where sigma is unknown, our test statistic when sigma is unknown, t equals x bar, this equation. So here's the equation right here, and you might notice that I've changed these values around a little bit. I'm having a little difficulty making the video for this problem, so I decided to restructure it so that the answer would be cleaner. Anyways, we can come up with our t statistic right here, so that's what we're going to do to find our sample test statistic. We have x bar, mu, and then we can come up with the numerator. Then we have the s, which is our sample standard deviation, and the square root of n. And then we also have our we can solve for our denominator. So we have, this is given to us. Mu is the mu from our null hypothesis, or that, threshold value, which is 0.25 in this case. So now we can determine our numerator, which is simply the difference, as you can see in the equation. And we have s, which is given to us, and the square root of n, which we know to be 5, but we'll put it into the equation. And now we have the denominator, which is simply s divided by the square root of n. Now we can solve for our t test statistic. So our t stat, or better set as our t value, is going to be our numerator divided by the denominator, and it's 2.492. So now we got to determine what the p-value is using that t-value from the test statistic that we just solved for. And the p-value is the probability that our sample of a more extreme sample. So probability of more extreme sample, and this is a two-tail test. So this was on, the upper tail, but when we assume that this is true in the first place, it's just as likely that we'd get this as a lower tail result, or we'd get an x bar that is much lower than the mu. So the probability of a more extreme sample is equal to the probability that our t would be greater than 2.492, or plus the probability that t would be less than negative 2.492. And basically what you'd be looking at, if you're looking at t distribution that's symmetrical, you'd be looking at the probability that t is greater than, this 2.492 value, the right tail, and the probability that it's less than the left tail. And these two tails have an equal probability, so the sum of these two probabilities is the same as 2 times the probability that t is greater than 2.492. So now we have to use our t-table to find what this probability is equal to. And the t-table is different than the z-table. When you look at the z-table, you have the z values on the x and y axis, and then the probabilities in the center. But in the t-table, you actually have your t values in the center and your degrees of freedom on this y-axis, and the probability on the x up here. So the first thing we have to consider is what is our degrees of freedom in this problem, and our degrees of freedom is always n minus 1. N is 25 in this case, so our degrees of freedom is 24. Now you want to look, so we want to look in this 24 value, and we want to find the t value closest to what we produced. So our t value that we found was 2.492. We go back to the t-table. Oh, it's right here. 24 degrees of freedom. Here's 2.492. So what's the probability that t is greater than that? Well, the probability that t is greater than 2.492 is 0.01, and that's the one you look in the one tail. Now, because the probability that t will be greater than 2.492, that's like a one-tail question. And then to find our p-value, because it's a two-tail test, we simply take that 0.1, which is this value right here, and we multiply it by 2. This t-table also has that calculation built right into it. Here's our one-tail 0.01, you just multiply that by 2, you get the 2.02. So since this is a two-tail test, we simply can use this 0.02 from the two-tail. So our p-value is 0.02 right here. Our value of our sample test statistic is 2.492, and a reminder, we used a t statistic instead of a z because sigma was unknown. So the population standard deviation was unknown. We have the sample standard deviation though, we use that, and when we have the sample standard deviation, we have to use the t distribution instead of the z. So when our p-value, in either case, when we use t or z, when the p-value is less than our level of significance, which is right here, we reject the null hypothesis and favor the alternative hypothesis. So that is A. So now as we can become concerned with the critical value approach instead of the p-value approach, we now solve the problem as if we did the critical value approach. Anyways, so the first question is, what is the upper critical value of the test statistic, and what's the lower critical value of the test statistic? If applicable, you have an upper critical value and a lower critical value because it's a two-tailed test. If this is only a one-tailed test, then there'd only be one critical value. And whether it's upper or lower would depend on whether the alternative hypothesis was it being greater than or greater than equal to versus less than or less than equal to. Anyways, it's two-tailed for us, so in order for us to find our upper critical value, we don't even have to look at the sample data at all. What we do look at though is what our alpha is. Our alpha is, or our level of significance, is 0.05, and this is a two-tail test. That's what we also have to be concerned with that when determining our critical value. And the last thing we have to be concerned with is since this follows a t distribution, is the degrees of freedom, which is equal to n minus 1, in this case 24. So we want to determine our upper critical value. We simply go to our table, our T table, and we say, oh, we have 24 degrees of freedom, so we're interested in this row right here. And the total probability that we're interested in is 0.05. And we can say that's distributed between two tails. So we can look at this 0.05 right here, and for the 24 degrees of freedom, we get an upper critical value of 2.064. So I think it was 2.04. Let me double check. Oh, 2.064. Great. And this is symmetrical, so you have to realize that your upper critical, this is a two-tailed test, so you have to realize that your upper critical value, T value, is going to be, you know, the positive of your lower critical value, or, you know, multiply that by the -1. So if you take -1 times our upper, we get the lower critical T value. And, you know, that's of the test statistic. T is our test statistic in this case. And now we say, oh, if our test statistic from the sample is greater than this upper critical value, then it's in the critical region. Or if it's lower than our critical value, then it's in the critical region. And in that case, we reject the null hypothesis. So we go back up and we calculate what our sample t-value is, and it's 2.492. That's greater than this upper critical t-value, and so our sample falls within the critical region, and what we want to do is we want to reject the null hypothesis. So now we have an upper critical value in terms of our test statistic was this t, and we have a lower critical value. So these are just two t values, but we also have an equation right here that you know, relates t to x bar. So if we have critical values in terms of t, and we also have mu, s, and the square root of n, then we can solve for, we can take these t values and we can find the equivalent x bar values. And x bar is in terms of labels. So we can also determine what the critical value is in terms of labels. And this is not just unique to the t distribution, but you could do this to the z distribution. You just use the z equation, and you'd use that when you know, s was unknown, but the population standard deviation sigma was known. Anyways, all we have to do to come up with the upper critical value in labels is we just take the upper critical value, t value, and we convert it to x bar. So we have this equation. We just need to form a new equation for x bar. And what that becomes is we have this original equation, and we can say that if we multiply this denominator on both sides, then we get t times s divided by the square root of n, and that's equal to x bar minus mu. So to get x bar by itself, we can just add mu to each side, and then we get mu plus t, our t value, times s divided by the square root of n, and that is going to be equal to x bar. So this is you know, the same type of progress that we did to when we were in chapter 7, I believe. Yeah. Oh, no. In Chapter 8, when we're doing interval estimations, the same kind of process. So we have what our mu, we can solve for what x bar is in this case. We have an equation right here. We have mu, or let's start out with TS, the square root of m, and our mu, and then we can find our x bar. So this equation just converts a t to an x bar, and since this t is a critical value, if we put this t value in here, then we get an upper critical value in terms of x bar. Anyways, s is always the same. Where is s? Oh yeah, it's given to us up here. Square root of n, right here, and then mu. And mu is, what we saw in the null hypothesis, which is 0.25. So we can find an equivalent x bar to this t value, in this case, by using this equation. It's simply equal to mu plus this t multiplied by the s and divided by the square root of n. And there we go. There's our x bar. So we have an upper critical value in x bar in terms of labels. So that is equal to this value right here, and I'm going to control and paste values. So to get the lower critical value, we simply do the same thing, but instead of using the upper critical t value and inputting into this formula, we use the lower critical t value, which is negative 2.064. So if I just drag this down here, our formula is the same. So we get our lower critical value in terms of x bar. And what's happening here is we have our mu, which is 0.025. The distance between, in this case, mu, or the middle number, is always z in terms of a t or a z distribution. In this case, the middle value is mu, which is 0.25. And the distance between 0.25 and the upper critical value will always be the same as the distance between 0.25 and the lower critical value. So we can test that and make sure that that is reasonable. So the distance between the upper critical value and mu is 0.12384, and then we can check the distance between mu and the lower critical value, and it's the same. So that's no surprise. And we can see that these is probably the correct answer. Well, it is the correct answer, but if you do this check, you would know that you probably got the right answer. Sorry, blabbling. So there's our upper critical value, and there's our lower critical value. And this was just a check, so we don't need to do that. I'll just get rid of that for my calculations, and that looks good. Oh, and last thing, so you got your upper and lower critical value in terms of x bar, in terms of labels. So then you can look at, just like in terms of your test statistic, you could now look at what your original x bar is, in this case 0.39952, and if it's in the x region in terms of x bar, which is greater than 3.7384 or less than 1.2616, then you also can reject the hypothesis. So in this case, x bar is roughly 0.40, and that is greater than this upper critical value, so you also know to reject the null hypothesis here. Alright, going down to the last type of problem, proportion problem. Basically, you'd like to prove that over 50% of all students in Stat210 have a grade below a C. So the null hypothesis is it's easier to look at the hypothesis the alternative hypothesis first. What we're trying to prove, in this case, we're trying to prove that P, which is a proportion of students with grade below C, is less than 50%. So that would be D, leaving the null hypothesis to be everything, the complement of that, which would be the probability that P is greater than or equal to 50%, which is A. So there we go, and now we can go ahead and find the value of the test statistic. It's a proportion, so we know it follows the Z distribution. We can use this right here, this equation. Now in this equation, your P bar is a probability is the proportion in your sample, whereas the regular P is your proportion from the null hypothesis. So we have P, we have P bar, and we have N, and we can come up with a numerator and a denominator and a Z statistic. So our P is 0.5, just like from the null hypothesis, and our P bar is the proportion in our sample, which is the number of students that has a grade below a C, and we divide that by the total number in our sample to get our proportion, our sample proportion. And we have N, which is the total number in our sample. That's 50. So now we can figure out the numerator. That is P bar minus P, and our denominator, which is P times 1 minus P divided by N. And then we need to take the square root of all of that. So there's our denominator, and now we can get the Z statistic. That's right there, and we can round this to 2 decimal places, and so Z is 1.41, and our alternative hypothesis is D, that P is less than 50. So this is a one-tail test, a lowered tail test or left tail test, and the p-value is the probability of a more extreme sample, which in this case it's only more extreme on one side of the distribution, on the lower side of the distribution, because we can only prove the null hypothesis not to be true if our sample is on the lower end. So our p-value is simply the probability that Z is less than negative 1.41, and we don't have to worry about the upper tail in this case. So we go to our Z distribution, look up negative 1.41, negative 1.41, that's right here, 0.07927, and Here's the value of the sample test statistic. Here's the p-value. And now in this case, the p-value, hold on. We need to put a level, I forgot to put a level of significance in here. We'll have a level of significance of 0.05. Now in this case, the p-value is greater than a level of significance, so we choose B. We do not reject the null hypothesis. And that's our conclusion. And if we were doing the critical value method, we would look at what our level of significance is, which is alpha. Right here, this is alpha. Or the level of significance, that's 0.05. And our alternative hypothesis is that p is less than, 0.50. So we say all of our room for error in this case is just in the lower tail. So we have to find the z critical value such that the probability of z being less than z equals 0.05, because all the level of significance goes in that left hand tail. And we can look that up in our table. So we want to look up 0.05 in the z distribution. It's in between these two right here. So I like to say that z is just negative 1.645 right in between these two numbers. Negative 1.645. And that is our lower critical value. This is only a left hand, a left tail test, a lower tail test. There's no upper critical value, so we're just going to leave that blank. And true or false, your sample falls within the critical region. Our sample is negative 1.41. That is greater than negative 1.645, so that is false. And our conclusion is B. We do not reject the null hypothesis. So